Friends, welcome to my YouTube channel. Dhanesh here. Today I am going to discuss on a recurrent neural network. This is the second video on a recurrent neural network. In the last video, we had a brief introduction. And we discussed in the last video we discussed the architecture of a recurrent neural network. In this video I will be covering first thing, what are all the characteristics of a recurrent neural network. Second one, the math behind recurrent neural network. Third one, backpropagation through time, training the recurrent neural network. Fourth one, vanishing and exploding gradient. Fifth one, why vanishing and exploding gradient happens in RNN. It's not happening in CNN. What is the reason? See, these 5 aspects I will be covering as part of this video. Let's start. See, in the last video as well, the one important aspect we discussed is RNNs are used to process sequential data. Very important. This is the difference between RNN and convoluted neural network. The recurrent neural network is used to process sequential data. Our feed-forward network can be used for example, convoluted neural network we are using for image classification. When we use for image classification, the current output has no relationship with the previous output. Or we can tell it as the convoluted neural network, or the traditional feed-forward network is not using historical data. It is not using historical data. But RNN uses historical data. The reason is RNN is used to process sequential data. If you want to know some of the examples where we need to process historical data, 1. NLP, natural language processing. 2. Speech recognition. Then even sometimes video and music sequence data. Fourth one, time series data. Stock market. In all these cases, we need to use historical data. So we have to use a recurrent neural network, not the traditional feed-forward network. Before getting into the math behind a recurrent neural network, I want to tell you about deep learning. I am not telling the traditional or the definition of deep learning. What is the mathematical interpretation of deep learning? Deep learning means you have a differentiable function. differentiable function which converts one type of variable into another type of variable. This is what happens in deep learning in all applications. If you consider regression, in the case of regression, this is regression. Here you convert a vector into a scalar. Vector is a second order tensor. You can take, this is a vector, this is a vector, this is a vector. Scalar is a first order tensor. This is a scalar. Matrix is a third order tensor with rows and column. Tensor means container for data, three-dimensional or n-dimensional array of data. Now, I will discuss some of the use cases to get more clarity on this differentiable functions, how we use to map data. One use case I can tell you is, first use case I am going to tell you is sentiment analysis. You may be familiar with this use case. In sentiment analysis, what we will do is, you have the RNN, this is your differentiable function. You will give sequence of data as the input and you will get output as a vector, whether it is a positive sentiment or negative. Here, this is the one use case we use RNN. The second use case, image captioning. Here you have the differentiable function, that is RNN, which convert a vector, that is your image, then the caption, that is the sequence of data, a vector into sequence of data. The second use case you use of the RNN's use. Now the third use case for RNN, it is language translation. Language translation. Here you have the differentiable function RNN, which converts a sequence of data into another sequence of data. In all these cases, we are converting one type of variable into another type of variable. That's what you need to understand. In all these cases, we are processing sequence of data. That means we use historical information. Now I am going to discuss about characteristics of RNN. When you consider RNN, one important point is, as we discussed, RNN remembers historical data. Concurrent recurrent neural networks remembers historical data, but normal feed-forward networks, they are not remembering, they are not using historical data. This we call it as parameter sharing. Very important. This is the first characteristics, parameter sharing. The second characteristics is in feed-forward network, each layer has its own weights and biases. That means the weights and biases are different. In a convoluted neural network, all feed-forward networks, the weights and biases are different. But RNN, it is the multiple copy of the same network, each passing a message to its successor. Hence, in RNN, all the hidden state weights, output weights, and input weights have the same value throughout all the connections. That means here the weights and biases are same. Very important. This is very, very important. This is the major design change in recurrent neural network, because it's a copy of each cell is a copy of its successor. Here the weights and biases are same. These are all the two important characteristics. One is it uses historical data. Second one, it is a copy of its successor. Each cell is a copy of its successor. So the weights and biases are same. It is also sharing. The parameters are sharing across the network. Now we are going to discuss about the math behind recurrent neural network. To understand the math, before getting into the math, I need to tell you, in a perceptron or a neural network, if you see, there are two aspects. There are two operations it will do. It will calculate the weighted sum. This is the first operation that is happening. If you see the math behind a perceptron, artificial neuron, we call it as perceptron. In each perceptron, first it will calculate the weighted sum. Then the second thing, it would be squashing it. Squash the weighted sum with an activation function. These are all the two processes we usually do in an artificial neuron. The same thing we are doing here as well, but only one difference. That difference is it is parameter sharing. It will share the weights and biases of the previous cell, or each cell at different timestamp will share the weights and biases of its successor. So that you need to keep it in mind. Now I will show you the architecture or the diagram. This we discussed in the previous video as well. If you see this diagram, here ht minus 1, it is a timestamp t minus 1. That is the hidden layer at timestamp t minus 1. It is getting a weight from its previous, its successor, that is wh. And you have the hidden layer at timestamp t, ht, and you have the hidden layer at timestamp t plus 1. But one important thing you can notice here is WH is same everywhere. Here the weights are same. And the bias BH is also same. I didn't show it in the picture. We are using in the equations BH as well. And as I told, xt minus 1 is the input at t minus 1. xt is the input at t, and xt plus 1 is the input at t plus 1. Yt minus 1 is the output at t minus 1. Yt is the output at t, and yt plus 1 is the output at t plus 1. And you can see the weights wi for different timestamp is same. And you can see the weights wo at different timestamp is same. And even the bias, I didn't show it in the picture, bi and bo also same. That is the design of, that is the characteristics of recurrent neural network. And you can see it's taking the parameter is shared. See the WH and the BH. BH I didn't show it here. It is coming to HT, the hidden layer. So the informations from the successor is shared. So that's all the architecture. Now I am getting into the mathematical equations. So I am writing the equations for the timestamp t. In the same way, you can write the mathematical equations for timestamp t plus 1 and timestamp t minus 1. So I am writing the equations for timestamp t. You can see it. At timestamp t, first I am writing the weighted sum z. Once again, I am showing the diagram. The weighted sum should be, you can see it here, it is wi input weight into xt, wi xt plus from the previous layer, the weight, the information, the parameter is sharing, the historical data, wh into ht minus 1 plus bias bh. I didn't show it here. So this is the weighted sum for HT, weighted sum towards the layer HT. Fine. So I am writing the equation. This is for timestamp time t. In the same way, you can write the equations t minus 1, t plus 1, everything the same way. So here z equal to wi into xt plus wh into ht minus 1, the parameter sharing. This is parameter sharing from the successor, plus bh. This, the bias, this I didn't show it in the figure. So this is the weighted sum. Now, what is HT? HT should be, we need to squash it. We need to squash it with the activation function. Let G be the activation function, then G into Wi xt plus WH ht minus 1 plus BH. This is for the timestamp t. In the same way, you can write the equations t minus 1 and t plus 1 as well. Now, I am writing the equation for the same time t. It is for time t only, but I am writing the equation for output yt. So you can see what is the output. See here, what would be the output yt. So I am writing that equation. So for that, so yt is equal to, again I am writing you the Z, the weighted sum Z should be, you can see it here in the figure, Z should be for YT, Z should be WO into HT plus B0. B0 is the bias for the output layer. I didn't show it in the figure. So the equation should be Z is equal to W0 HT H suffix T plus B0, bias of the output layer B0. Now to get the output YT, again you need to squash it with an activation function. Normally we use softmax to get a probability range of 0 to 1. You know that. Then G into again W0 HT plus B0. So this is the math behind recurrent neural network. Now I am getting into one important aspect, that is backpropagation through time. Backpropagation through time. It is BPTT. Backpropagation through time. See, recurrent neural networks uses backpropagation algorithm for training. For training purpose, we use backpropagation algorithm. That you know. But one difference here, we have to apply the backpropagation for every timestamp. That is one major difference. Hence, it is known as backpropagation through time. Now, I am going to write some of the important equations in backpropagation, gradient descent and backpropagation algorithm. The first equation you are familiar, it is W of, for weight, W of I plus 1 is equal to Wi minus alpha into dou E by dou W. This equation you know. For bias, B of I plus 1 is equal to Bi minus alpha into dou E by dou B. Here alpha is the learning rate, ranges from 0 to 1. You know it. So these are all the equations you need to use it in backpropagation algorithm. You know this. Now, backpropagation algorithm, as you know, it calculates the gradient of the error function or loss function or cost function with respect to the neural network's weights and biases and find out the global minimum of the cost function. Here, the equation will be dou E by, I am writing with respect to weight. The same process you can repeat for bias as well. Here, the one important point is the historical data, the previous data, that is time span. So the equation is sigma t is equal to 1 to capital T dou Et divided by dou W. This is the mathematical equation for dou E by dou W. As you know, the backpropagation algorithm, we uses chain rule. You know that. So the chain rule, as you know, chain rule means this is chain rule dy by dx equal to dy by dp into dp by dx. So this is equivalent to dy by dx only. So here the chain rule becomes, you need to understand this math. This is equal to, we can write it as dou E by dou W, the partial derivative of error with respect to weight, is equal to sigma T is equal to 1 to T. Then we need to apply the chain rule, dou E by dou of YT, the output Y at T, into dou of YT divided by dou of HT into dou of H suffix T divided by dou of HK. This is, I will explain you, this is very important, into dou of HK divided by dou of W. So here this term you need to understand. It is the partial derivative of hidden layer at time t to time k. This term, see this chain rule, you know, you are familiar in backpropagation algorithm. So finally, as you know, this will be cancelled and this will be again cancelled, and finally you will get dou E by dou W. But this term dou HT, the time is different. This term we call it as this term involves the product of Jacobians. This is little bit complex math. If you are interested, you can listen. This term we call it as the product of Jacobians. It is a determinant. The Jacobian, it is a determinant matrix, its value determinant. It is a determinant. This Jacobian determinant, you can again expand it as dou of HT divided by dou of HK is equal to dou, again chain rule will come, dou of HT divided by dou of HT minus 1 into dou of HT minus 1 divided by dou of HT minus 2, etc. into dou of HK plus 1. Here it is K plus 1. You can see it here, suffix K plus 1 divided by dou of HK. This term, why I am explaining, if you can understand this math, you please understand, otherwise it's fine. Why I am explaining this Jacobian determinant is, if you see, if you learn this Jacobian determinant, the term grows exponentially. This term grows exponentially. This we need to use it in the next part, vanishing and exploding gradient. This term grows exponentially with respect to the eigenvalues of the determinant. This is one of the reasons for the vanishing and exploding gradient in, recurrent neural network that we will discuss in the coming section. So this is the backpropagation through time. Next, we are going to discuss about vanishing and exploding gradient. You try to understand these equations. Some complexity is there, that if you see what is a Jacobian determinant, it's easy for you to understand. Now I am getting into the vanishing and exploding gradient. What is vanishing and exploding gradient? See, there are two issues associated with backpropagation in RNN. They are vanishing and exploding gradient. Vanishing gradient means if the weights are small, the gradient shrink exponentially. This is known as vanishing gradient. Exploding gradient, if the weights are big, the gradient grows exponentially. This is known as exploding gradient. Now, why vanishing and exploding gradient happening in recurrent neural network, not in convoluted neural network? I am going to explain you that. That's the last part. We have to understand why vanishing and exploding gradient. Why it is not happening in a recurrent neural network. From the mathematical explanation for backpropagation through time, you might have understand, Jacobian determinant and its exponential, growth from this. That is the one reason. So now I am going to discuss in detail what is the reason behind this vanishing and exploding gradient in RNN. It is not happening in convoluted neural network. See, the gradient coming from the deeper layers have to go through continuous matrix multiplication because of the chain rule and the Jacobian determinant. If they have small values, they shrink exponentially until they vanish and make it impossible for the model to learn. This is known as vanishing gradient problem. While on the other hand, if they have the large value, they get larger and eventually blow up and crash the model. This is exploding gradient. This will cause your RNN unstable and unable to learn from training data. For example, so why it is happening in RNN? I will give you an example. The reason is, one is, as I discussed, it is used to learn long-term dependencies. Long-term dependencies. Let us assume that our RNN is used to process some data for language translation from English to French. English to French. So English, it starts like, let us assume that we can assume that it starts like John, is from France. Then we have a lot of, sentences. After that, it's an example I am telling. The translation is from English to French. The paragraph starts with John is from France. Then you have a lot of sentences and it's, a lot of words are there. Then finally, it's given John speaks. Let us assume that, around 1 lakh words are between these two sentences. John speaks, then we need to predict that data. At that time, our recurrent neural network has to travel a lot. The error signal needs to travel backward through this entire pathway in backpropagation algorithm. This we call it as long-term dependency. Because of this long-term dependency, this multiplication, finally, when you use the chain rule, if the value is very small, when you multiply it, what will happen? It becomes very small. If the value is very large, when you multiply it, it becomes very big. This is vanishing and exploding gradient. That is the first reason for why it is happening in RNN, why it is not happening in CNN. It is the long-term dependency for language translation, this type of use cases we use. The second one, as I discussed, in the backpropagation algorithm, the Jacobian determinant. Here the eigenvalue grows exponentially. Dou ht by dou hk, this grows exponentially. You can learn this Jacobian determinant, Jacobian matrix, then you will get more clarity. Now, the third reason I can tell you, in CNN, the weights and biases are different. So, for example, when you are doing the backpropagation in a particular layer, the weight is less, then it will cause a, it will cause somewhat like a gradient, vanishing gradient, but it is compensated in the next layer. If the weight is high, that is compensated by the exploding gradient. Since the weights and biases are different in the convoluted neural network, they compensate each other, they cancel each other. The vanishing gradient and the exploding gradient in the different layers will cancel each other. But the design of recurrent neural network, here the weights and bias are same, that is the design, so it grows exponentially. So how we can solve this vanishing gradient and exploding gradient? That we will discuss in the next video. Thanks for watching.